Origin of Boyle's law. The pressure on the walls of the container is the result of billions of collisions of molecules with the walls. So these molecules keep on hitting the walls, and that's how the pressure is built on the walls. As you can see right here, you can see that the pressure is too, the volume is too low right here. So the molecules try to move around and hit, the possibility of hitting the walls is much higher because of the low volume. So they keep on hitting the volume, they keep on hitting the walls, that it will have high pressure. At the same time, you can see that this has the larger volume, so it has a larger space to, the molecules have larger space to move around, so they have a less probability to hit on the walls, that's resulting low pressure. Molecular motion and temperature. The absolute temperature of a gas is proportional to the average kinetic energy of its molecules. So for gas molecules, even at 0 degree Kelvin, it would still possess a small amount of kinetic energy. So they keep moving even at the 0 degree Kelvin, which is at the absolute temperature. The molecular motion and the temperature. The compression of a gas increases its temperature. So whenever you compress any gas, the temperature of the gas would increase. And if you expand the gas, then the temperature would decrease. The gas molecules are in constant motion because of the collisions result in no net loss of energy. If the temperature is a measure of average molecular motion, then compressing a gas should cause its temperature to rise. So we already knew that when you compress a gas, the temperature would rise, and when you expand it, the temperature would decrease. So when you can see that in this case right here, when you are trying to increase the pressure right here, the molecular energy increases, and here you are trying to increase the volume and decrease the pressure right here, so the molecular energy will be decreased. So it means this compression is increasing the molecular energy and expansion is decreasing the molecular energy. Why molecules keep on moving? The macroscopic objects lose kinetic energy due to friction, which is transformed into heat. Microscopically, heat is a molecular motion. Thus, the friction between the molecules would result in molecular motion, and there would be no change. Heat transfer. Heat transfer is always from hot to cold objects. So the heat always transfers from hot object to cold object. It happens in three different ways. One is conduction, second one is convection, third one is electromagnetic radiation. So let's look at the conduction. Conduction is a way of transferring hot or heat to colder objects. That is nothing but heat is transferred by molecular collisions. So let's say that you have lots of molecules around in a room. So one hot particle goes and hits with the other hot particle, and the heat will be transferred from hot particle to cold particle. Now the second particle becomes hot, and the second particle goes and hits the another particle which is cold, and it makes other particle hot. So finally all the particles will become hot. So this is called the conduction mechanism. So the second type is convection, in which heat is carried by the motion of volume of hot fluid. So in the conduction, it is done by the molecular collisions, and in the convection, it is a group, or it is a volume of the fluid will be, or the one which would be transferring heat from one to another set of, or no, one of the volume of fluid. The third one is electromagnetic radiation, in which heat is transferred by electromagnetic waves. An example is the rays coming from sun. So electromagnetic radiation, the heat is transferred from sun to the earth by these electromagnetic radiation waves. So here's the picture which shows you that the example of conduction in the at homes, the heating is done by the conduction, and the traditional AC or heating units is done by the convection. and then the radiation, the electromagnetic radiation is from sun to earth. Thermal conduction, mostly it happens in solids. Thermal conductivity is usually the metals are the good conductors of thermal conduction, and examples of these thermal conductors are gold, silver, and copper. And the ones which do not let the heat flow through them are called the thermal insulators. And examples of thermal insulators are wood, cork, air, snow, and styrofoam. Convection usually happens in liquids and gases. Example, we all know that the warm air rises up, so that's why, like, whenever any air or in a group of the air particles, if they become hot, they always rise up. And convection currents in the atmosphere are the examples of the convection mechanism. Radiative heat transfer, example, the sun, all the objects radiate and absorb the energy. If more energy is absorbed than radiated, then its temperature rises. If less energy is absorbed than the radiated, then the temperature falls. Intermolecular attractions between the molecules of liquid are stronger than those in gas, but weaker than those in solid. So let's say that if you have molecules in a solid, the attraction between the particles of solid are stronger than the particles in the liquid. In the similar fashion, the attraction between the liquid particles is much stronger than the particles of gas. The molecules of solid do not move freely about but vibrate around fixed positions. Since the molecules in solid are very tightly packed, they won't have too much room to move around, so they just vibrate in their own positions. Both liquids and gases are considered as fluids when we are talking about convection. So you can see in this picture right here, solid, all the particles are tightly packed, and in the liquid, they have a little bit of space. You can look right here in the gas, the molecules are separated at a huge distance. Changes in phase. Energy is either consumed or released by a material during a phase change. So if a material is converting from solid to liquid or liquid to gas or gas to solid and so on and so forth. So in order to change from one type to another type, they either have to release the energy or consume energy to get that physical change. Adding or removing energy does not cause a temperature change, but helps in a phase transition. So whenever we add energy or remove the energy, the solid material, let's say, it will convert from solid to liquid, but the temperature of the solid will remain even when it is going to convert into liquid. But if you give after it turns into liquid, if you keep giving the energy, then its temperature would rise. But in the beginning, when you're giving the energy, so that energy will be solely used to change its phase. Evaporation occurs when fast-moving molecules in liquid leave the liquid surface and escape into air. Evaporation is a cooling process. So always evaporation happens from the uh, surface, and the molecules escape from the surface of the liquid. As you can see in this picture right here, you have water container with water and container with the alcohol. So when evaporation happens, it happens from the surface. And you can see right here, the molecules in here are escaping, but at a slower rate compared to alcohol. So the evaporation process depends on what material it is, and it is a natural process. It happens no matter what the temperature is. So at every temperature, this evaporation keeps on happening, but at particular temperature, it could be more, or at some temperatures, it could be less, but it's an ongoing process. The boiling point temperature. The boiling point of a liquid is that the temperature at which the molecules of the liquid attain enough kinetic energy to overcome the intermolecular attractions resulting in a change of state from liquid to gas. So whenever there is any boiling point happens, then it would be breaking the traction between the molecules, and now the liquid becomes gas and it would escape into the atmosphere. Difference between evaporation and boiling. Evaporation differs from boiling in two ways. Evaporation occurs only at the liquid surface. Boiling occurs in the whole entire volume of the liquid. Evaporation occurs at all temperatures. Boiling occurs only at particular temperature. For example, boiling point temperature of water is 100 degrees Celsius. So whenever the water reaches 100 degrees Celsius, the whole entire volume of the water would keep boiling. Water vapor versus steam. For temperatures below the boiling point, we speak of water vapor. The temperatures above the boiling point, we call it steam. So the temperatures before, which is less than 100 degrees Celsius, we call it as a water vapor. The water vapor is still not at 100 degrees Celsius. So right after 100 degrees Celsius, all the water which is becoming gas, that is called steam. Heat of vaporization. The heat of vaporization of a substance is the amount of heat energy needed to change 1 kilogram of substance from liquid to gas at its boiling point. For example, it takes about 2,260 kilojoules of energy to change 1 kilogram of water into steam. So, in order for changing 1 kilogram of water into 100 degrees Celsius or above steam, it takes 2,260 kilojoules of energy. You can see in this picture right here. So let's say that you have 1 kilogram of water and it is at 100 degrees Celsius temperature. And if you give 2,260 kilojoules of energy, whole entire volume of this liquid will become steam and whole entire thing would have been evaporated. So let's look at one of the examples of heat vaporization. Compare the heat given to a person's skin when 1 gram of water at 100 degrees Celsius falls on it with the heat given by 1 gram of steam at 100 degrees Celsius. Assume that the skin is at the normal body temperature of 37 degrees Celsius. So they want to find out what is heat given to a person. So let's look at it. So heat, we know that is Q is equals to mc delta T. And they want to compare with the 100 degrees Celsius steam to 37 degrees Celsius skin. So the temperature difference is 100 minus 37, that's going to be 63. So let's look at the first, which is the 0.1 1 gram of water, and which is at 100 degrees Celsius. So now look at it that no, if it is at 100 degrees Celsius, in order for it to go from 37 to 100 degrees Celsius. So let's see that it's going to mc delta T. M is the mass of the water and C is the amount needs to this specific heat, and this is 63. So when you calculate it, it's going to be 0.26. And now this 0.2 for every 1 kilogram, we need 2260 kilojoules of amount of energy to make it to complete steam. But we have only 1 gram, so how much energy, how much heat energy is needed? That is going to be calculated as 0.001 times 2260. Then you get 2.26. So the total energy, heat energy would be transferred to the skin is nothing but 0.26 plus 2.26, the total of 2.52 kilojoules.